Okay, so we go on to our next talk now. This one is by Tobias Felkl, who is a PhD student working with Mikhail at UNSW. So in a sort of related domain, only now we're talking about new physics from B to S new. So thank you, Tobias, for agreeing to be part of this as well, and take it away.
Yeah, thank you. So before I start, I would first like to express my gratitude for this really nice opportunity to present our recent work here in this seminar series. And so this is a paper that appeared only this week on the archive and that I was involved in together with my supervisor, Mikhail, and Locke, who is going to start his PhD in Hong Kong quite soon. So a brief motivation, as the title of our work already suggested, we're concerned with the transition of bottom quarks into strange quarks and the simultaneous emission of neutrinos in that process. In the standard model, those processes get mediated by diagrams such as the ones you can see here. So because of the fact that the flavor of the B quark changes, but not the electric charge, we refer to this as a flavor changing neutral current, which happens to be suppressed in the standard model due to the fact that there is no neutral boson which could mediate these processes at tree level. And so there also always has to be a loop structure. And then another suppression mechanism called the GIM mechanism kicks in, which is basically due to the structure of the CCAM matrix in the standard model. So these processes are rare in the standard model, and this is convenient because we also would expect the effects of new physics to be small. And so this is a suitable setting, so to say, to look for new physics. There are two advantages in these processes, especially in the case of neutrinos in the final state, namely that those can be enhanced by new physics, not only on the intermediate level, where new physics would take up the role of what are the Z bosons and W bosons in the standard model, but they could also enter in the form of final states, which escape undetected if they have properties similar to those of the neutrinos. And in fact, in our work, we took into account the possible existence of massive sterile neutrinos. Another advantage is that since neutrinos are electrically neutral, the amplitudes of these processes completely factorize into a hadronic and leptonic part, and therefore they are under very good theoretical control. From an experimental point of view, in most cases, the related observables have not been measured yet. They are only upper bounds, but the Belle II experiment is projected to measure them with an uncertainty of only about 10% or so, with a full integrated luminosity. There's one exception for this charged decay mode here of a B plus meson to a K plus meson and two neutrinos. One can derive this weighted average if several analyses are taken into account. And the central value here indicates towards an enhancement on top of the standard model prediction by a factor of 2 or 3 or so. So I hope I convinced you that it makes sense to look at these processes and that they are interesting. And with that, let me move on to the content of my talk, which is a brief introduction of the effective field theory framework that we're using. Then I will introduce the observables that we took into account and discuss the results, first only in the case of massless neutrinos and new physics contributing to 1 or 2 operators at a time. And then I'll mention a few aspects coming with massive neutrinos. And finally, I will draw conclusions. Right, so we are concerned with the decays of B mesons, which are constituted by a bottom quark. Therefore, it makes sense to divide up the particle content of the standard model into a kind of light sector, which includes the bottom quarks and all the particles which could emerge as decayed products in these processes, and heavier mediators, which can appear at the intermediate level, but not as final states. Because of this quite pronounced mass gap between these two sectors, it is possible to kind of remove the heavier particles as active states from the theory and instead capture their effects entirely in terms of so-called Wilson coefficients, which we denote by the capital C's down here, which accompany effective dimension 6 operators, which are entirely composed of the light particles in the standard model. And so this effective theory has the suggestive name low energy effective theory. And so since we want to consider sterile neutrinos as well, we add them to the particle content here. So this is a very convenient and model independent approach, since the Wilson coefficients now do not only capture the effect of the standard model, but also all sorts of new physics can be parameterized in terms of it if the relevant scales are sufficiently larger than the bottom quark mass. Okay, so what effective operators do we have available? We can distinguish them in terms of their Lorentz structure. There always is a neutrino bilinear and a quark bilinear. And so we have either vector operators, scalar operators, or tensor operators. And in the case of vector or scalar operators, we can draw a further distinction based on whether the projector in the quark bilinear is left-handed or right-handed. So we have 5 operators available here, but only one of them gets a sizable contribution in the standard model, which is the left-handed vector operator. If you plug in the numbers, then you get a contribution which is about 0.01 inverse TV squared here. But new physics could now in principle give rise to all of these operators. And then there might be interference with the standard model if it contributes to the vector operators, either the left or the right-handed one. In that case, the effects will be a bit different. Okay, so let me go through the observables that we took into account for our analysis. So we generally distinguish between neutral decay modes and charged decay modes, especially because the current bounds are a bit different for those. Right, so the first observable that we looked at was the decay of a B meson to a scalar kaon. And since in that case, we only have one visible particle in the final state, so to say, there's only one observable available, which is the branching ratio. We also looked at the decay of a B meson into a vector K meson, which has an additional polarization degrees of freedom and which decays into a scalar kaon and a pion normally. So that means that we have 2 final state particles available, or equivalently, there's additional or independent information available which can be extracted by a measurement of the so-called longitudinal polarization fraction, which is prospected to be possible at Belle II. We also looked at the inclusive decay mode, which takes into account all final states which carry a constituting a strange quark. So for the predictions of these observables in the standard model, one needs form factors which take into account all the QCD part of the interaction, which is not calculable from first principles. Therefore, what we did is we used the results that can be extracted from a combined fit to lattice QCD data and light cone sum rules. So for the decays B2K, we used the results from this paper, and from the for the decays B2K star, we used another one that you can see down here. In order to calculate the uncertainties that come with the predictions, we used the flavor physics package Flavio developed by David Straub. Right. The standard model prediction for the inclusive mode is also cited and can be looked up in this paper here. We chose to present this one here because it takes into account sub-leading contributions, which we don't in our code. So this is the predictions for the current constraints. One can refer to several papers published by the Belle II collaboration. This one down here is a bit older. This is from Aleph. And for the projections now, one needs to go to the Belle II physics book. And indeed, with a full integrated luminosity of 50 inverse autobahn, we see that the uncertainties are projected to go down to about only 10%, under the assumption that the standard model predictions get confirmed in the future. And this is what we also will assume in order to directly use these numbers here, which are available. Okay, so this table now summarizes our results for the current constraints on and the future sensitivities to new physics under the assumption that first, neutrinos are massless, and also new physics only contributes to one operator at a time, or dominantly only one operator at a time. So another assumption that we make is that the Wilson coefficients are always just real numbers, and we evaluate these constraints here at the scale of the Z boson mass. So the first column contains a representative selection of operators which can get sourced by new physics and which get bounded in different ways. The first 2 vector operators here would interfere with the standard model because the neutrino flavor indices are fixed to be either just 1, 2, or 3. Whereas if you have gamma or delta here, these are in principle arbitrary numbers, but they should be unequal. This makes sure that, for instance, in this example here, we have a vector operator which does not interfere with the standard model. We also have scalar operators for which the final state neutrino flavors can either be equal or unequal. And we have tensor operators for which it can only be unequal, because tensor operators are anti-symmetric in the neutrino flavors, whereas scalar operators are symmetric. And this means that if there's a contribution to a channel signified here by gamma delta, there will also be a contribution to the channel delta gamma with equal strength. And therefore, the bounds on these operators will be a bit more stringent in general. Right, so what you see is that here, so in the second column here, we summarize our results for like a conservative upper bound on the absolute value of the Wilson coefficient in inverse TV squared. So the least stringent bounds arise for the interfering vector operators. Then we get more stringent bounds for scalar operators, and the most stringent ones for the tensor operators, which again is partly due to the symmetry properties that these operators exhibit. So in order to build physical intuition, we also recast these upper bounds on new physics, Wilson coefficients, into very rough estimates for lower bounds on the associated scale for new physics. And you see that currently new physics up to a scale of at least a few TeV may be seen as partly constrained. Right. So the next column here summarizes the respective observables, which gives rise to the bound, which is indicated here. And what one can see is that this is always B2K in the case of scalar operators, both currently and also in the future. For tensor operators, it is always B2K star, which gives rise to the most stringent bound. This is also projected to be the case in the future, whereas for vector operators, the situation is not so clear. So there's no overall trend towards one clearly most competitive observable. And therefore, we indicated both processes here for the prospective bounds as well. So these future sensitivities, again, are derived under the assumption that Belle II will indeed confirm the central values of the standard model predictions. And so now you can compare the values in this column here to the ones which hold currently. And the most impressive improvement can actually be achieved for a right-handed vector operator, which does not, a right-handed vector operator which interferes with the standard model contribution, which is due to the fact that in there, the leading order contribution to the observables will already occur at linear order in the Wilson coefficient, not at quadratic order, but there can't be efficient cancellation of the standard model contribution either. The latter can, of course, happen for this operator here, which is sourced in the standard model as well, and therefore this bound is much less stringent. So for the scalar operators, the improvement factor is about 5, whereas for the other operators, it's about 3 or so, or a bit less. And this means that this will potentially push up the bounds, the lower bounds for new physics, up to a realm of, depends, maybe 20 or even 30 or 40 in the case of scalar and tensor operators, which is quite an impressive improvement. Right. So this was the case of just one operator at a time, but we also wanted to know what happens if we can switch on both of them simultaneously. And for that, we produced some plots. So I should probably first explain the legend here in order not to get lost in parameter space. So the solid lines, both in violet and in dark green here, indicate the current bounds that can be derived for the parameter space based on existing data on B naught to K star naught and B plus to K plus. Now for the future, we want to indicate the regions which are predicted to be compatible with a confirmation of the standard model prediction. For that, we used shaded regions for B2K and B2K star. So orange stands for B2K and blue stands for B2K star. And we also have dotted and dashed lines in black for the inclusive mode and in pink for the observable FL. We also distinguish between the case of just 5 and 50 inverse autobahn via either light or dark shaded regions and for the inclusive mode, lines being either dotted or dashed. Right, for the inclusive mode, we assume the sensitivity of 50% and 20%, or I should rather say an assumed uncertainty, experimental uncertainty. Right, so we assume that standard model predictions get confirmed, and that means that if the contributions from new physics is just small enough, this will always in the end turn out to be compatible, or apparently compatible with the results, meaning that there will always be a region containing the point 0, 0 in parameter space, which remains viable. And this is this one here on the left and this larger one here on the right. So the difference between these two plots in general is that on the left, we have interference with the standard model contribution, whereas on the right, we do not have that, but in either case, we have contributions to vector operators. And since we have interference with the standard model, what can happen on the left is that new physics contributions effectively just flip the sign of this Wilson coefficient pertaining to the left-handed vector operator, which has zero measurable effect if it's the only new physics contribution. So this gives rise to this viable region here as well. Another difference between the two plots is that here we have this excluded white region turning up in the middle of the structures here, in the middle of these straight bands, and in the middle of this ellipsis here. And this just reflects our assumption again that destructive interference cannot be too efficient, because otherwise we would just kill the standard model contribution and Belle II would not measure anything. Right. We see that in the case of interference with the standard model, we have two more viable regions up here and down here. What happens in there is that new physics would effectively relocate the source of the source for all these processes here from the left-handed vector operator to the right-handed one, which would also appear compatible with standard model prediction. So we have 4 disjoint windows for new physics, so to say, which will remain viable in the future. And the latter two, like the latter two that I just referred to, could be interpreted as being kind of induced by physics that one may expect to reside roughly at 10 TeV. So I've been talking about B2K and B2K star a lot, but I would also like to draw your attention to the inclusive mode, indicated by the black lines here, which already under the quite conservative assumption of an uncertainty of 50% can be expected to probe almost exclusively parameter space, which has been inaccessible so far. So we always land within the region indicated by the solid lines. And depending on where you are in parameter space, it is less prone to cancellation than B2K and B2K star are. Right, so let me now move on to the case of massive neutrinos in the final state. So far, they have always been considered massless. And for that, we again chose a representative selection of Wilson coefficients and plotted them as functions of the mass of a sterile neutrino in the final state. So on the left here, we have 2 final state sterile neutrinos with equal mass. So that means that halfway through the available range here, there's already no phase space left available. So the right-hand side of this plot here remains white in that sense. Whereas on the right here, we just have 1 massive sterile neutrino. So you can occupy the whole range. So the gray shaded area here indicates the areas in parameter space which are already excluded by current bounds. And then the orientation of the hatching indicates what observable we're talking about. And the future sensitivities are indicated by the lines, be them either dashed or solid. So a very generic effect of massive neutrinos in the final state is a phase space suppression of the decays, meaning that there's less transferred momentum available for the kaon, and it means that these decays will be more suppressed in themselves, and therefore the Wilson coefficients can be a bit larger, which means that the bounds will weaken. Right, so in the case of vector operators here, what one can see is that our earlier observation that B2K and B2K star are kind of similarly competitive is only true for quite light neutrinos, whereas when you crank up the mass, you see that B2K will become completely dominant as well for larger neutrino masses. Okay, in the case of scalar operators, the situation is as clear as it was for massless neutrinos. B2K is always clearly the most competitive observable of the entire neutrino mass range, and scalar operators also remain more stringently constrained than vector operators, regardless of where you look at the bounds. And lastly, we have tensor operators, for which it is also the case that B2K will become the most competitive observable for quite heavy sterile neutrinos. But if you remain below 4 GeV or so, B2K star is the superior process. And in that range, tensor operator will also retain its status as the most constrained among the operators. And here it turns out that the inclusive mode is also a quite suitable probe. And in fact, it is superior to the mode B2K if the sterile neutrino is light enough. Okay, so that's my last slide. Another effect of massive neutrinos is the following. So we generally want to have operators which annihilate a bottom quark and create a strange quark, and for that we need a quark flavor ordering SB. But one could also choose the ordering BS and then apply a Hermitian conjugation, which in the case of scalar or tensor operators refers to operators which are genuinely independent of those with SB ordering. And now these two classes of operators can interfere if both neutrinos in the final state are massive, because only in that case, neutrinos carry both chiralities. And that's important because the Hermitian conjugation here implies that the chiralities in the neutrino bilinear get flipped. So we specify a mass of 1.5 GeV here for the final state neutrinos. And so on the left here, we show a situation where we have two left-handed scalar operators. So we have the same chirality, whereas on the right, there's a right-handed scalar operator here and a left-handed scalar operator down here. So the chiralities are opposite. The most conspicuous difference is that the orientation of these ellipses pertaining to B2K star and to FL flip the orientation. So measuring these observables could in principle help distinguishing between these two scenarios of the same or of opposite chirality. One of course has to admit that B2K is still more sensitive because we're looking at scalar operators, but in slightly more involved scenarios, it is easily conceivable that B2K might be a bit further suppressed. And then the combined viable parameter space will indeed carry information about the chiralities of these interfering operators here. Right, so with that, let me already draw conclusions. We have seen that the combination of B2K and B2K star is indeed a very powerful probe of new physics in all considered scenarios. If one just looks at single operator bounds, we found that if the neutrinos become large enough, in the case of sterile neutrinos, it will always be B2K, which is the most sensitive probe. But in the case of vector or tensor operators, if neutrino masses get smaller, at some point B2K star will be more competitive. And in either case, the inclusive mode is also quite suitable for probing the parameter space. On the other hand, scalar operators can be probed in the scenario of interference between SB and BS operators, so to say, regarding the quark flavor ordering, if the final state neutrinos are massive, and then one could measure B2K star or FL to distinguish between the chiralities of the scalar operators. One last aspect I didn't have time to go further into today, but it turns out that if one wants to interpret this current weighted average of results for B to B plus to K plus in terms of new physics, it turns out that scalar operators provide the most compelling explanation for that. And I would be happy to answer a question if someone has one in that regard. But first of all, I would like to conclude and thank you for your attention.
Thank you. Thank you very much. Let's have, we've got, plenty of time for questions now. So Ines, do you have a question?
Hello. Thank you for your talk. I was wondering if you looked at, so when you were discussing the use of beta K star and beta K, was there anything compelling with considering the ratio of the two? Like, did you find that there was anything like that you could simplify, I guess maybe theoretical calculations?
No, I think in general you can't, because the form factors and all this stuff is different. So
yeah,
I'm not sure, but I don't think there's that kind of independent information that you, or like game information you could get.
Cool. Thank you.
Arjun.
Yeah, actually.
Yeah, maybe I asked that question on the last point. Tobias, if you clarify that a little bit more.
Sure. So for that, I will bring up a backup slide. Where is it? Right. So, so there have been analyses have been performed by Belle II, and Barbar, and you can. So what has been done in a recent publication by Belle II is a simple weighted average was computed, and this indicates this kind of current central value for B+ to K+ with an uncertainty. And so if one compares this number to the standard model expectation, one sees that it would signal, or it would indicate an enhancement of a factor of 2 or 3 on top of the standard model prediction, if substantiated further. And so what we did is we indeed interpreted that as a hint for new physics, and proposed a scenario of the standard model extended by a massless sterile neutrino. And then we compared which of the different new physics operators could explain it kind of most compellingly. Meaning that we first computed the value of the Wilson coefficient that one would need in order to explain this number here. And then with these Wilson coefficients, we also calculated the predictions for the other decay channels, B2K star, both the current and the both the neutral and the charge mode and the inclusive mode. Right, and if then one confronts this with the existing bounds on these processes and standard model predictions, one finds that scale operators are arguably the most compelling solution, because the uncertainties are fairly small. It is well compatible with all the bounds. It is a bit larger than the standard model predictions, so this will definitely be tested, and that's all nice and good. For vector operators, it's also viable, although there is some tension with existing bounds in the case of B2K star not. And for tensor operators, well, I mean, it's not so appealing because the contributions must be huge. There's lots of tension with existing bounds, and also the uncertainties are so large that it's compatible with 0 at less than 2 sigma. So that is, I don't know, let's say unclear what to make of that. And we of course need more data and more experimental results to clarify it, but currently it looks like, well, scalar operators could be an explanation for that. But yeah, right, it's a very tentative or like very preliminary.
Yeah, interesting. And what happens with the massive neutrino? It's not compatible, or
now? So we assume that massless sterile neutrino for simplicity. I mean, you could also introduce a mass, but that would probably just mean that you would have to increase the values of the Wilson coefficients a little bit, because the decays are phase space suppressed then.
Okay.
Yeah.
Okay, if anyone has any questions, feel free to shout out. But looks like there isn't, so I think I will